Okay, so I'm going to share my screen and I'm going to try to, because I've got this up. So, this is the homework stuff, but if we go to the ebook, sign in, and so let's just go to the ebook. Okay, so for example, here are the chapters, right? So let's just take a look and so let's do chapter 4, for example. Unless you want to look at determinants.
We can start with chapter 4.
Okay, so chapter 4. So for example, let's just go to section 4.1. Let's view the e-text, okay?
Okay.
It's taking a little minute. I think I'm maxing out my my Comcast internet with all these connections. Okay, so do you ever just read the book?
Sometimes.
It can be helpful. I know it seems silly, but it actually really can be helpful.
Okay.
Like important things. And they've got great pictures in the book. So I do encourage you. Let me move this over here to look at the book. Like this explains why u plus v looks like this vector. For example, when u is this way, and then we put v on the end of u, and then we see what the vector looks like starting at 0 to this very point right here. That tip, you can think of that point as being u plus v, or this blue ray as being u plus v. See what I mean? So
Hmm.
they've got some really nice pictures, but I'm going to just keep on going. I'm going to actually I'm going to look for the menu. Okay, so here's the menu for chapter 4, but it should give us, I'm kind of looking for a better menu. I'm actually looking for the page that the exercises are on because, so anyway, so let's just scroll through until we get to the exercises at the end of the section. Because if you're looking for, and really the pictures are amazing. So here are a bunch of exercises.
Okay.
And the answers to the odds are in the back of the book.
Okay.
So for example, let's look at let's look at number 9, okay?
Okay.
And it asks if H is the set of vectors of this form, where the first coordinate is just S and the second coordinate is 3S. It's not letting me select. And the third coordinate is 2S. Find a vector V in R3 such that H is the span of V. Would you have any idea how to work that?
Um, I can't remember how to like start it.
Okay, so my point is, hey, you need more practice, right? So I'm gonna look for the search bar, and I'm gonna look for answers to odd numbered exercises. Okay. And it's not, I don't, all right, let's see what comes up. All right, there we go. Odd numbered exercises. It's in Appendix 1. Exercises A11. Let's just go to that. Okay. So here are appendices. Answers to odd number problems. See it
Mhm.
right here?
Yes.
All right, so let's try to click on that. Or we'll just, gosh, it would be really nice if I could just click on that, wouldn't it? Maybe I need to continue in the app, but I'm afraid to even try. Let's see if we can find. answers to odd number problems. Once we do, we can bookmark it. Like you should do that in your book, is bookmark answers to the odd numbered problems. I'm just going to keep going until I get to the appendix. Or maybe if I use the table of contents.
Yeah.
So there are a bunch of exercises. You can do an interactive exercises, right?
Okay.
Okay, so let's just see if we can find appendix 1. Note to students. I'm gonna go back here to the table of contents. Oh yeah, we're at the very beginning. Okay, appendices. There we go. Answers to odd number problems. All right, now that's a clickable link. Okay, great. So now that we're at the beginning of answers to odd numbered problems, right? We want to get to the chapter 4 answers.
Hmm.
Okay. So, we keep clicking till we see chapter 4 stuff. And then we can bookmark it. Like this is section 1.8, right? So I'm gonna just jump forward until we get to answers to odd number problems. And then we'll go back and we'll try to work that problem.
Okay.
Wow, I really hate this. Okay. So that's chapter 2, section 1.9. It's still balking. All right, I'm just gonna wow, it's still jumping around. I'm gonna stop. 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 All right, I'm gonna put in like A30 if it will let me. Oh, good Lord. Answers to odd numbered problems. All right, so now down here, I'm going to put in like a 30 to try to jump forward. Let's see if that works. A30. And I'm
Okay.
going to hit enter. Great, that worked. So that's already section 6.6. So that's a little too far, right? So I'm going to go back to like 24, okay, and hit enter.
Mhm.
And let's see if that's okay, that's better. So maybe back to 18. Basically, all right, there we go. All right, this is section 4.1 answers. All right. So section 4.1 answers. So what we can do is you can add a bookmark there. See this little symbol?
Mhm.
You probably know how to do this better than I do. But the point is, okay, there's the answer to number 9. All
Mhm.
right. But now I want to go back to problem number 9 in chapter 4. What were we in? 4.1 or 4.2?
I think it was 4-1.
And I should probably bookmark that too. Yeah, so I'm going to bookmark that too. All right, now how do we find our bookmarks?
Under the bookmark tab.
Are they in our notebook?
On the table of contents, there's like little like tabs at the top.
Bookmarks.
Mhm.
Fantastic. So we could even label these bookmarks. So A17 is where 4.1 is. So I
Mhm.
suppose, so, and then this is page 208 that we're on.
Mhm.
But there must be a way to, I would like to be able to rename that bookmark, but I don't know how. Do you know how to rename a bookmark so I could say exercises 4.1 or something instead of just page 208?
I don't think so. I don't.
All right,
I,
there's got to be a way to do that. But anyway, here we are. So let's work on this number 9 problem, okay? So I'm going to write it down. And my point is this. You're saying, you just feel like when you sit down to work the problems that you don't know what you're doing, right? And the way to get comfortable is to just practice, practice, practice. Literally sit and try. All
okay.
right, so I'm going to stop sharing and I'm going to pin this.
Okay.
All right, so this was the problem. We're looking at a set H, and they were vectors that looked like this. But I think we understand S has to be some real number. Does that make sense?
Yeah.
So find a vector V such that H is the span of V. All right.
Okay.
Now, let's just recall what it means for us to ask about the span of a single vector. Like they didn't write the problem like this. They just wrote this and said H is a space, and then this is a kind of vector that looks like this. And when we write H in set brackets like this, we really are saying H is the span of E, but let's just recall some important things to understand about span, okay?
Okay.
Okay, so if we have one vector, call it V, then what is the span? Well, the span of V is literally the set of all scalar multiples of V. It's everything we can build using V. Well, what can we do with V? We can add bunches of copies of V to itself, which is a scalar, an integer scalar multiple of V, right? Or we can maybe even weight V with something that's not an integer, like 1.5. The span of V is the set of constants C times V, where C is a real scalar. Let's just stick to the real number line for right now, okay?
Okay.
So if you have one single vector V, its span is basically the whole line that V lives on. Shall we draw a picture?
Okay.
Yeah, part of being able to quote unquote do problems is to understand the language. So let's say this is V, okay? This red vector, okay? Or we could think of V as the point at the tip. Or we could think of V as the ordered pair whose coordinates are that point. Or we could think of it as the vector. You know, we could think of V as the vector where the first coordinate is the x1 coordinate, right? X1 axis, which we usually just call X, you know, when we're doing geometry, X2 axis is what we used to call Y. So you can think of V as array. We can think of it as this point, or we can think of it as a column vector, okay?
Okay.
Now, the span of V is literally all the ways we can multiply V times a number. For example, look at minus V. Minus V is on the same line as V. It's the same length as V. It just goes in the other direction. Does that make sense?
Yeah.
Well, where would 2V be? Well, 2V would be the same direction as V, but twice as long.
Okay.
Okay? And in fact, 1/2 V would be the vector that goes from 0 to 1/2 of the distance. So the span of V is this entire line.
Hmm.
Span of V, if we think about the geometry, is a line. The line on which V lies if V is not equal to the 0 vector. If V, so that's, you know, what it is. If it's just, now, if V is just 0, if it's just the 0 vector, which if we drew it here would just be this point here, then the span of V is just the zero, because when you multiply zero by any scalar c, you just get zero. And so the geometry of the span of V when V is zero is that the span of V is the origin. It's just a point.
Mm, okay.
Now that's if there's one vector. We're trying to understand span, right? But what if we have two vectors? Say U and V. Then the span of UV is the set of all linear combinations of U and V. What does that mean? It's the set C1 times U plus some weight, call it C2, times V, where again, C1 and C2 are just scalars, real scalars. And so as long as neither of these is zero, if U is not equal to zero and V is not equal to the zero vector, then the geometry of the span of two vectors is the plane.
Okay.
As long as U and V are not scalar multiples of one another. Because if they're scalar multiples of one another, they live already on just the same line. And if they're living on the same line, then all you can build with that set is just that line. So if U is not zero and V is not zero, but U and V are scalar multiples of one another, like maybe U equals 3 times V or something like that, then the span of U and V is the same as the span of just U, which is the same as the span of V because they both build the same line. But if U and V aren't scalar multiples of each other, that means they go in different directions. They don't build the same line. So we can draw a picture of that, where U and V are not scalar multiples. So U not equal to zero, V not equal to zero, and U and V are not scalar multiples of one another. That means when you draw the picture, you can still draw it in 2D. It's about as far as we can go. Let's say U is here. But let's say that V goes off in a different direction. Maybe it's even a different length. The span of U and V is the plane. Because you can find any point in this plane by taking an appropriate scaled version of U and adding an appropriate scaled version of V. It's the X1, X2 plane, if they're not on the same line. So and then this idea of span just gets bigger and bigger and bigger. The more vectors you have, the potentially higher dimensional space you can build. If you've got three vectors in three space that go off in three different directions, then you can build all of three space using those. So in general, if a set of vectors, let's just say we're going to call these vectors v1, v2, v sub n, is linearly independent. That means you cannot build any of those vectors by using a linear combination of the other vectors. Okay, there's no linear dependency relation. Do you remember the definition of linearly independent?
Um, I don't remember the exact definition, but
All right,
I
I'm going to give it to you, i.e., the only scalars that make this equation C1 V1 plus C2 V2 plus plus C sub n V sub n equal to 0. The only scalars that make this equation true are C1 equals C2 equals equals C sub n equals 0. And here 0 is the real number. Here 0 is the vector.
okay.
But here's, we're thinking of 0 as the real number 0. All those, so it means if you build a matrix and use these vectors as the columns, if we construct a matrix A using these vectors as its columns. So again, it's about, being able to understand and write the language of linear algebra. So how would we write that? We would say A is equal to square bracket. Okay, and we would put V1 here, and that means that's the first column. V2 here, no commas or anything. That's the second column. But then to indicate there might be some columns in between. And then V sub n, it would be the last column. So that's what we mean when we write that. We're using these vectors as the columns. You understand that?
Mhm.
I mean, does that notation look familiar?
Yes.
Okay, so for these vectors, V1 through Vn, to be linearly independent means that if we construct this matrix A, when we row reduce A, we find a pivot in every column. And what does that mean?
That means like when you row reduce, like
Yeah, no free variables. That
or
means AX equals 0 has no free variables or parametric variables. Every variable is a basic variable with a pivot. And that means this system doesn't have any free variables. That means AX equals 0 only has the trivial solution, X equals 0. All those things mean the same thing. Those vectors being linearly independent means when we row reduce, we don't have any free variables. And that's the same thing as saying X equals 0 has only the trivial solution, X equals 0. Just that one single solution.
okay.
But that's really what this means. This equation right here, that is the columns of A being weighted with scalars. Those scalars weights are the coordinates of a solution X. If the only way to get this equation to be 0 is for all of these coordinates to be 0, That's the same thing as saying that this vector x is only the zero vector, that it's the only thing that will work. In other words, x looks like the vector where those coordinates, these scalar multiples, are the weights, right? So they go as the coordinates, they go into x as its coordinates.
Mhm.
And what we're saying is the only way we can find an x with these kinds of coordinates that make this sum equal to zero is if all those coordinates are actually zeros. And that's the same thing as saying x is the zero vector is the only solution to ax equals zero. Does that make sense?
Yeah.
Okay, so that's a good review. Well, let's go back to this set now. This is section 4.1. And we have vectors that look like S, 3S, 2S. And we want to find a vector V such that H is equal to the span of that V. So it's just one type of vector. Can we tease out a vector from this vector? Can we tease out sort of the underlying vector? Can we factor out something from all of those coordinates?
Yes, the S.
Yes. And that leaves a vector that looks like what?
032. That was
That's
the
not a zero.
not a zero, one. One, three,
Yes, the other
two. Yep.
zero. 132. That is our V. Because by definition, this this set where S is a scalar is by definition the span of this vector that we're calling V. That's what the span of that vector is. It's all scalar multiples of that vector. So this would be your V.
Okay. That was a lot more simple than I thought it was going to be.
Right, right. And of course, you can count on me to get there the long way.
No, but I appreciate the like in-depthness because I need it.
Well, there's a lot going on. Do we want to maybe look at a problem from the next section?
Yeah, like discriminants. Is that the next section, or are you talking about the same chapter?
Determinants?
Yes. Why did I say discriminants? My
Don't
brain.
worry, we're gonna, well, in some, because you know why? Because in class, we talked about the fact that the determinant sort of does help us discriminate between square matrices that are invertible and square matrices that aren't. Let's just review a few things from chapter 3. In some sense, the determinant determines whether or not the matrix is invertible. Okay, so for chapter 3, we only play the determinant game with square matrices. We'll call it the determinant game. Do you know what that means when I say square matrices?
Yes.
Same number of rows as columns. So it's an n by n. So there's two things that can happen. If the determinant of A is zero, the number zero, it's a number, then A inverse does not exist. And when we row reduce A, there is not a pivot in every column, but that's the same thing as saying row here because it's square and has the same number of columns as as rows. So if there's not a pivot in every column, there's not a pivot in every row. And so just tying this back into things that we learned earlier, and this means AX equals 0 has non-trivial solutions. That means solutions other than x equals 0. Solutions other than just, now, x equals 0 always is a solution, okay? But we'll have some other ones. So that's one thing it means. It means ax equals 0 has non-trivial solutions. A inverse does not exist. And it also means that there are free variables
Mhm.
because we don't have a pivot in every column. There are free variables in ax equals 0. And that means the columns of A are linearly dependent because if there are free variables, then we can solve and tease out some vectors that will be a description, an explicit description of of the solutions to ax equals 0. The columns of A are linearly dependent. I always put that in capitals so that we don't accidentally misread it. But if the determinant of A is not equal to 0, A inverse exists. Columns of A are linearly independent. And AX equals 0 has only one solution, namely X equals 0. So in some sense, the determinant is a discriminating value. It lets us discriminate whether A is going to be invertible or not, which tells us so much about A.
Mhm.
So we have numerous methods for calculating the determinant. So shall we look at some of those?
Okay.
Let's just list some of the tools that we have. We can use cofactor expansion. If there are lots of zeros, that's a good way to go. But sometimes just having lots of zeros isn't enough because it might still be kind of, a pain. We can use row operations and do bookkeeping to make sure that we keep track of how any row operations affect the determinant. And we can literally, well, it seems like literally, but it's really using one of these row operations where we can factor out a scalar from all of the entries in some particular row to make the other operations easier, whether they're cofactor expansion operations or row operations. Okay. So for example, if we are asked to find the determinant of A where we're looking for, let's say that there's a 4 here, a 2 here, a 6 here, and a 2 here, and a 0, and a 0, and a 0. That's kind of looking good for maybe cofactor expansion along that first column, right? But it really depends upon what all's going on in here. If we have 5, 10, -15 there, and we have 0, 3, 9 here, and we have 2, 0, -4 there. We're trying to find that determinant. There are a couple of different ways to go, but let's just think ahead, okay? So, we see a lot, oh geez. Ah, Rocky, my dog. I've got this whole jury rig thing with my phone, like sitting in a jar with this book thing, and oh my gosh. I'm just trying to, you know what I need to do? I need to bite the bullet and buy one of those like things with legs that holds a phone up,
Uh,
for like a selfie.
yeah, like a little tripod.
Yes, that's what it's called. I need to buy a tripod. I think I'm going to go on Amazon and get a tripod because this is ridiculous. And now it's like you can just see the top of my head. Anyway, so listen, if we do cofactor expansion along column 1, why don't we try that and see what happens, okay?
Okay.
Do you know what I'm talking about when I say cofactor expansion along the column?
So cofactor expansion is when you like multiply it, like not multiply it, but like you. Why don't you explain it? Because I don't want to sound.
All right, let's just review. Now,
I don't.
this is where
I
it's
think I
really
know
nice
what it
to
is.
have the notes in front of us.
Yeah.
Hang on. I'm going to go to the I'm going to go to the class notes. I'll share my screen with you because even I have to be careful when I try to write down a definition like cofactor expansion. There's so many ways for that to go bad. So let's go to the class notes and let's look at what Dr. Good wrote, or we could go into the book. Cofactor expansion was section 3.1 and 3.2. Okay, so let's look at those class notes. All right. All right. So if we have a matrix, and this is just a way to indicate a matrix where the entries are, indexed with their row number I and their column number J. The IJ cofactor is the number that we get by multiplying -1 raised to the I plus J times the determinant of the matrix that we get when we delete row I and column J from the big matrix A. So let's go back. We've reviewed that here. All right. So AIJ, I think I did. Oh, yeah. We define AIJ first. So AIJ is the submatrix of A that we obtain by removing row I and column J from A. Okay, so here's an example. Here's an A. A12 would be what we would get from A if we deleted row 1. See, I've kind of gently crossed it out with red, and delete column 2. So if we delete row 1 and column 2, what's left is a 3 by 3. Does that make sense?
Yeah, I remember
All
this.
right. So cofactor expansion depends upon the idea that we know how to find the determinant of a 2 by 2 matrix. So if we can kind of chip away at a big matrix until we're just looking at a bunch of little 2 by 2 matrices, then we can build back up to calculate the cofactor expansion values. And then that expands to be the final determinant of the whole big matrix. All right. So because because this particular formula that's shown here at the bottom as the definition of the determinant is kind of ugly, it's not a very pretty one, talking about the fact that you can calculate the determinant of A by expanding along the first row. So the entries would be in row one. So we get that formula, okay? But that's nasty. So this is the idea. If we talk about a number which is -1 raised to the I plus j times the determinant of ij, then it gives us a really, really pretty way to define the determinant of A as an expansion along or across row one. But it turns out we can expand across any row I of A and we'll still get the determinant. Or we can expand down any column J of A and it'll get us the determinant. So here's our example. All right, and it says find the determinant of A. So the first thing we do is we see, ooh, there's lots and lots of zeros in this first column. So we're going to expand down column one. By definition, the determinant of A is this number, which is the 4, times the determinant of the submatrix that we get when we delete the row and the column that 4 sit in. See what I mean? So
Yeah.
we would delete row 1 and column 1, and then we get a 4 by 4. And all of these other terms in the cofactor expansion down column 1 are going to go away because we'll be multiplying all those by 0.
Hmm.
You see? Then we say, ooh, we've got another column with lots and lots of zeros. Let's expand down that column again. So we keep the 4, but now we take the 2 and we multiply it times the determinant of the 3 by 3 that we get when we delete the first row and the first column, because that's what the 2 sits in. You see what I mean? And then we keep doing that. And that worked out fine because look at where the zeros were. We had it's almost upper triangular. The only place we didn't have a 0 was right here, but this very last little matrix down here in the corner, well, that turns out to be a 2 by 2, and we know that the determinant of that is A times D minus C times B, right? So 2 times 0 minus -2 times -8, which turns out to be -16. And then we have kept track of these numbers, the 4, the 2, and the other 2, right?
Hmm.
And it turns out to be really nice. Okay. So
Yeah.
see the class notes. I don't want to write all those down. I don't have that much time. We've only got like 15 more minutes. But here, it's not quite as pretty, but I'm going to go ahead and do it with you. All right. So the first thing we do is we say we got lots of zeros there and probably enough zeros that the rest of it won't be too horrible. And it's good practice anyway. We're going to expand down column 1. All right. So the determinant of A is going to equal. Now, just remember that if it's like a 4 by 4, this is the way the signs go. Start with a plus in the upper left-hand corner. Then it goes minus, plus, minus, minus, plus, minus. They all alternate, and that tells you what sign these different terms are going to be. But this is up in the upper right, so that's a plus. So it's a plus 4 times the determinant of the 3 by 3 that we get when we delete the row and the column where the 4 sits. So tell me what to write for my rows for
Um,
this 3 by 3.
so it's gonna be 5, 0, 2.
All right.
Oh, sorry,
That's
I
fine.
was going
That's
up and
fine.
down. 10, 3, 0, -15, 9, -4.
Great. Now, we don't have any row or column that has 2 zeros, but it's not so bad to have 1 0 and 2 regular ones. So
Mhm.
why don't we just look at that? Now it turns out that these, actually, you know what I want to do? I want to change 2 numbers, and I'll tell you why. Because I'm going to put a 2 here, excuse me, I'm going to put a 3 here and a 0 here, and I have a reason for that, okay? Just
Okay.
trust me, because I want to show you where the sign actually has to change. Okay, so now we're gonna use cofactor. Oh, but that makes us want to use cofactor plus minus plus minus plus. Ooh, it makes us want to use cofactor expansion down there. So I'm going to do this. I'm going to actually make it not any better. All right. So we can either do cofactor expansion down column one, or we could do cofactor expansion across row three. Shall we do that?
Okay.
You see what I mean? We've got 1, 0. It's going to be 6 of one and half and dozen the other. But if would you rather do the column or the row?
Um, Maybe the row?
Okay, we're going to expand across row three just so that we get something different going on, right?
Okay.
Now we have to keep this 4. We can't lose it. Now, to expand across row three, we take, well, 0 times the determinant there, but we don't need that because it's going to be multiplied by 0. But it's plus minus plus minus, you see, because this is a 3 by 3. And when it's a 3 by 3, there's a minus there.
Okay.
So plus minus plus minus. So this is going to be a minus 2 times the determinant of the matrix that we get, the submatrix that we get when we delete the row and column that this 2 is in. So you want to tell me what that matrix is going to look like?
Yes, it's gonna be 5, 3, negative 15, and 9.
Great. And then we have to keep going. And so plus minus plus minus plus. So it's plus a negative 4 times the determinant of the 2 by 2 matrix we get when we delete the row and the column that the negative 4 are in. So what is that? 5, 3, 10, 3? And all of that gets multiplied by 4. Are you following?
Yes.
So suddenly it's a lot more work if you don't have like lots and lots and lots of zeros, but that's okay. We can still do this. Now there is an easy way to find this determinant because it turns out we can multiply 5 times 9 minus 3 times negative 15. We can, but I just want to show you there's another way to do this. We can factor the 5 out of this first row, and we can factor the 3 out of the second row. And then we're looking to find the determinant of the matrix that looks like 1, negative 3, 1, 3. And that's
Okay.
a lot easier.
Mhm.
See what I'm saying?
Yeah.
Same way here. Before we calculate the determinant of this, and this idea actually goes here too, because if you look at the solutions to quiz 3 when I post them tomorrow, I worked that quiz by factoring out common factors from 4 of the 5 rows, which just made my calculations much easier. And I also used row operations. So you'll have an example of using row operations to look at. But I'm going to pull the 5 out of row 1 and the 3 out of row 2. And now we only have to calculate the determinant of this little matrix. And that's going to be a lot easier.
Mhm.
So here we go. It's 4 times, okay, so negative 2 times 5 times 3. What is that? Negative 30 times 1 times 3 minus negative 3 times 1. And then this will be a minus, what, 60 times 1 times 1 minus 2 times 1,
Mhm.
right?
Yeah.
So it's 4 times negative 30 times, what is this? 3 plus 3? Is that
Mhm.
6?
Mhm.
This is a minus. So it's minus a minus. So
Yeah.
it's 3 plus 3 is 6. And then we've got minus 60 times 1 minus 2, which is negative 1. So we've got 4 times what? Negative 180 plus 60. So that's 4 times negative 120, and that's a grand total of negative 480. And the beauty of these is you can use your calculator to check. Do you know how to do that?
Yes.
Now that's using cofactor expansion, but there is a much easier way. The easier way to work this, I think, is to use row operations, but first make our life. So this is solution 1. Solution 2 is to just factor out those common factors from each row so we get lots of leading ones. It makes the row operations easier. I don't like to play with fractions because it's just too easy to make a mistake. So we pull a 4 out of row 1, so we'll be pulling out, no, we can't pull out a 4, we can pull out a 2, right?
Yeah.
We pull a 2 out of row 1, we pull a 5 out of row 2, we factor out a 3 from row 3, and we factor out a 2 from row 4. Now we're looking at 2, 1, 3, 1, 0, 1, 2, negative 3, 0, 1, 1, 3, 0, 0, 1, negative 2. Any way you slice it, even if you go ahead now and do cofactor expansion, which you could do, it's just easier. Just remember that this whole thing has to get multiplied by the determinant of this. But let's do row operations, okay?
Okay.
This first column is already cleared, right?
Mhm.
So I'm just going to clear below this pivot. So what's the row operation that we could do to get rid of this 1?
Um, to
How about row 3, because that's the row we're going to replace.
yeah.
Always start with the row that you're going to replace, minus row 2. Can replace row 3. Do you agree?
Oh, yes.
Great.
I always overthink it.
Yeah, I know. Don't. You don't want to overthink it. It's not fun. So 2, 1, 3, 1, because we're not changing the first row. 0, 1, 2, negative 3, because we're not changing the second row. In fact, I'm
Mhm.
going to go ahead and write down the fourth row as well, because we're not changing it. And that just leaves me no room for error. I know I'm replacing the third row, and I'll always write the row that I'm replacing first.
Okay.
Okay, so 0 minus 0 is just still 0. Good. We didn't screw that up, right? So
No.
1 minus 1 gets us a 0 here, and that was the point, right?
Mhm.
What's 1 minus 2 going to be?
-1,
And what is 3 minus a negative 3 going to be?
0. 3 minus 3.
3
Oh,
minus
3
a
minus
negative
negative
3.
3.
We're
6.
subtracting this row from row 3.
6.
6. Great. Ooh, so now all we got to do, this is a pivot. It's not a leading one, but it's still a pivot position, is get rid of this 1, turn it into a 0. Then we'll have an upper triangular. And we'll
Mm.
be able to use the rule that says if you have an upper or lower triangular matrix, you can just take the product. But we got to remember to keep these numbers. Let's not forget these. What was this? 10 times 6 is 60. So it's 60 times whatever this turns out to be. Okay. We can't forget these factors that we factored out. All
Okay.
right. So what should we do? We're going to replace row 4. So we take row 4, and what do we do with it to get a new row 4?
Can we add row 3 to row 4?
What?
Can we add row 3 to row 4?
Yes, let's add row 3 to row 4. So row 4 plus row 3 will be our new row 4. I always write the row that I'm replacing first.
Mm.
All right, here we go. 0 plus 0, 0. That's easy.
Mm.
0 plus 0, 0. Now what happens here?
That turns to 0.
That's what we wanted. And what happens here?
It will turn to 4.
Great. And now we have an upper triangular matrix. We haven't used any row switches, and we haven't done any scalar multiplying because we did that sort of at the very beginning.
Mhm.
So there's no change in the determinant from a row replacement operation.
Okay.
So now The determinant is going to be 60 times the product along the diagonals. 2 times 1 times -1 times 4. So we should get the same answer. So this is -8. What's 8 times 6? 48. So 8 times 60 is 480. Is that what we got before? Ooh, that's a good sign. It's always a
Okay.
good sign when you get the same answer twice. Hi, David. I've seen you in the room this whole time. I'm glad you came to visit.
Yeah. Well, I came to ask,
I
like, 'cause I have
can't
like
hear
issues.
you.
Oh, you can hear me?
Hang on, let me turn up my speaker. All right, try again.
So, can you hear me now?
Yeah, I can hear you.
Okay, so I came originally because like I had issues with my printer, and I was gonna ask you if I could just do this on like a note page or something, like for my notebook. But um
Did you read
yeah,
the
I just ended up
announcement? Did you read the announcement?
yeah, I just read it, and I was doing it while kind of like listening.
Yeah, I think the easiest way to do that one, and that this is the hint I gave everybody after I said let's do it as a take home because it was taking too long, is first do the factorization and then use row operations. Now, if one of your row operations is a row switch, it changes the sign. You have to multiply by -1 out front. If one of the row operations you do is a scaling, like if you scale a row by a particular number, then whatever you scale that row by, you've got to multiply the determinant by that.
Yeah. Well, I did it with the row operations.
Okay, good. And you can use your calculator to check.
Yeah.
Great. So let's keep doing these Zoom office hours because we covered a lot of kind of basic concepts as well as doing a couple of specific problems. Do keep using the book, and bookmark the appendix where the answers are to the odd problems and just practice more problems.
Okay. Yeah, that was also really helpful. I'll definitely use the book for like reference to and for practice.
Do you have you used an e-math book before for any of your classes?
Um, Not really since this semester. Like there's been like a book option, but the teacher has never really like actually used it.
Yeah, it's a different story with an ebook. It's, in some sense, it's maybe a little more convenient because you can read your book, without having your book with you. But there's a downside to an ebook. It's a little harder to navigate.
Yeah, sometimes.
All right, I have an appointment with another student at 7:30. I've promised to meet one of my discrete math students. So I'm going to have to close out this office hour. I'm sorry.
No problem. Thank you for being able to meet and helping me out.
You're very welcome. Let's do this again. Let's not wait too long.
Okay. Thank you.
David, I'm glad you joined.
Yeah, I am too. Yeah, it kind of just made things easier.
Yeah, I'm going to stop recording because I want to ask you a question.